So we want to talk about a few applications of the calculus of vector valued functions. And the first is arc length. So recall, this is something that I'm sure you've seen before. So if y is a function of x, the arc length, or the length of the curve from x equals a to x equals b is given by, well, you integrate from a to b, and what do you integrate? You integrate the square root 1 plus, you take the derivative and square it, dx of that. Yeah, and so this represents if I have a curve, here's A, here's B, well, this is the length of the curve from here, adding up all that distance to there. So we have a very similar formula for a curve parameterized by a vector valued function. So it has a very nice form, and it's, this works for being, this is of course in a plane, but it also works in space too. So the length of the curve, just say r of t, from, well, now we have 2 points in time, so t equals a to t equals b. Well, all you do is you integrate the magnitude of the derivative. And this has a really cool interpretation. So if we think about r of t being the path of a particle, then the length of the curve is just finding the distance that the particle traveled from time a to time b. And how do we do that? Well, we just integrate or add up all of the different speeds along that path. So it's actually really nice to remember. So let's see why that's the case. Well, if I have a curve like this, okay, given an orientation, so here's t equals a, over here's t equals b. And so if you remember how we did it for just y equals f of x, what we do is we take a little piece of the curve and we linearize it. What I mean by that is we just take a little segment like that and we call it ds. And so the length of this little segment ds by the distance formula is just the square root of dx squared plus dy squared plus dz squared. So if we zoomed in, we would see something like this. Here is ds, and then we have our x component, our y component, and our z component. And so this little segment just has all three of these little components. We can put ds and I mean, really we're just finding the length of this vector dx comma dy comma dz, and here it is. Okay, but what is dx dy dz? Remember, this curve is parameterized by a parameter t. And so what do I really mean by dx, a change in x? What I mean by dx is I mean x prime of t dt. This is just like the chain rule. Or, I mean, you probably talked a little bit about differentials in Calc 1. So dy is just y prime of t. So you're just measuring the change along the tangent line. Okay. Z prime of t dt. Okay, so if I plug all of this in, notice that ds is really just and all of these have a dt squared, which we can factor out as dt. And so if I want the arc length, we'll notice first of all that this is the length of the derivative vector. So to find the arc length, I just add up, well, what I mean by add up is integrate these little pieces ds from a to b, but that's just the same thing. It's going from a to b and t of r prime dt. So there's the arc length formula. So we've sort of already been using a little bit of intuition about the motion of a particle, and that a vector-valued function traces out the path of a particle. So now let's zoom in specifically on the dynamics of just the motion of a particle in space. So let's say a particle moves in space. I mean, it could be in the plane, but it's really the same thing, according to some vector-valued function. And this is really kind of the heart of what's going on in all the applications. We have a particle and it's moving, so at any given point t, we have an output vector that's telling us where the particle is. So this is the position vector of the particle. Well, the velocity is, and we'll use v of t for velocity, it's just the time derivative of the position vector. And then the speed, or recall that speed is the magnitude of velocity. So that's just the length of velocity, which is just the length of the derivative. And then the acceleration, is, well, we'll say a of t. Well, that's the derivative of velocity, which is the same thing as the second derivative of position. So this is kind of just reinforcing a lot of our intuition, but we'll just kind of say it once and for all, that when we do some applications with particle motion, this is really fitting right into what we've seen before, like in Calc 1, but now we're kind of moving through space instead of just moving along a line like we did in Calc 1. All right, so we want to find the length of this helix from t equals 0 to t equals 10. So if we call this vector valued function r of t, we actually know the answer. Well, we just integrate from 0 to 10 of the absolute value of the derivative, dt. All right, excellent. Okay, so what is r prime of t? Well, it's 3 cosine t minus 3 sine t, and then 1, like that. Okay, and then what's the length? Well, it's going to be square root of 9 cosine squared t plus 9 sine squared t plus 1 squared. But something amazing happens, right? So cosine squared plus sine squared is 1. So what are we left with? We're just left with 9 plus 1. So square root of 10. Well, that's about as easy as it gets, right? So we integrate from 0 to 10, the square root of 10 dt. So that's just square root of 10 t, evaluated from 0 to 10. Well, t is 0 gives us 0, so we have 10 times the square root of 10. That's the length of this helix. Remember that a helix goes kind of like this. So it's kind of the length of this particle, or the distance the particle moves as it kind of winds up this cool little helix shape like this. Okay, so we have the position of the particle. We want the velocity, speed, and acceleration at t equals 2. But we'll start by just finding just those values as a function of t. So the velocity, I guess we can call it v of t. It's just the derivative of r of t, which is minus e to the minus t, e to the t, 0. Okay, so the speed is just going to be, okay, this squared plus this squared. Well, this is 0, so just that's going to be e to the minus 2t plus e to the 2t, just the square root of that. And then the acceleration is just going to be e to the minus t. What's the derivative of the velocity? So that just gives us that. Okay, so at t equals 2, v2 is just minus e to the minus second, e to the second. The speed at 2 is just the square root of e to the minus fourth plus e to the fourth. And then the acceleration at 2 is e to the minus 2 e squared 0, like that. Okay, so easy enough. Okay, so we want to know the maximum height and the distance traveled by this ball that's thrown from an initial height of 1 meter, an initial velocity of 4 meters per second, and let's see, we're assuming the acceleration due to gravity is negative 9.8 meters per second squared. We're also assuming, this isn't written, but we're assuming there's no drag force or anything like that. Okay, so what do we do? Well, we want to realize that we know the acceleration vector. So what's the acceleration in the x? Well, there is no acceleration in the x. And the acceleration in the y direction is negative 9.8. That's gravity. So gravity is accelerating us downwards. So here's our acceleration vector. So if we want to know the velocity vector, well, the velocity is just, well, I'm just going to integrate the acceleration. But my constant that I get, so the constant in the x and the constant in the y, is just going to be the initial velocity in those directions. So my antiderivative of 0 is just a constant, and that constant is the initial velocity in the x. Well, my velocity is 4, but that's 30 degrees above the horizontal. So if I draw kind of a right triangle, my velocity in the x is going to be 4 cosine 30, and my initial in the y is going to be 4 sine 30. This is just, I'm just putting this vector, velocity vector, in component form, the initial velocity vector. So this is just going to be 4 times cosine of 30 degrees. And then this is going to be, well, I need an antiderivative. That's negative 9.8t. And then plus the initial, plus my constant, which is the initial velocity in the y, which is 4 times the sine of 30. Okay, and then I can do it again. My position, well, I just take an antiderivative. So 4 cosine of 30t plus my initial position in the x, which I'll just say is 0. So let's set this to be the origin right there. And then the y, well, here this is going to be t squared over 2. So that'll be negative 4.9 t squared plus 4 times sine of 30 t, and then plus my initial position in the y, which is 1. Okay, so there is my position vector. All right, so now I'm ready to start answering the questions. Well, to find the maximum height, I need to know when the maximum height occurs. So notice that the max height occurs when the y component of the velocity is 0. Why is that? Because that's when the particle is going to turn around. It's going to go up here, and then up here the velocity is going to be 0 and go down. But we can just solve that, and what do we get? Well, we get approximately, so I'm just going to set this equal to 0, the y component of the velocity, and we get approximately 0.204 seconds. And so if I plug in r of 0.204 and take the y component, so what I can do, remember our component functions here, this is like x of t, y of t, so I just want y when t is 0.204 but this gives me approximately 1.204 meters. Okay. And then next I need to know, when does the ball hit the ground? So ball hits ground when y is 0, and we also want t to be positive, right? Because this is kind of a parabolic model, so it's also going to hit the ground back here, but it doesn't actually hit the ground back there. It only hits the ground up here, but that's when t is positive. So over here, t is going to be positive. And so we just set this equal to 0, and I just used a calculator. We get t is approximately 0.700 seconds, and then that horizontal distance, well, I just want to plug in 0.700 for x, and what do I get? Approximately 2.424 meters. So there's the distance the ball travels before it hits the ground. There's the maximum height. Alright, so a particle moves along a circular path given by this vector value function. We want to determine the velocity, speed, and acceleration, and then show that the velocity is always orthogonal to the acceleration. Okay, so what is the velocity? Well, it's just the derivative, so it's going to be minus a. So I should say that a is going to be the radius of the circle. This looks like a W. It's actually omega. That's the angular velocity, so that's how fast the particle is moving around the circle. So it's omega. That's just using the chain rule there. So we take the derivative, and here we get a omega cosine omega t. Okay, so there's the velocity. What's the speed? Well, the speed is the magnitude of the velocity. But notice that I'm going to get a omega squared sine squared plus a squared omega squared cosine squared. But the sine squared plus cosine squared is going to give me 1. So I'm just going to have the square root of a squared omega squared, which is a omega. That's the speed. So the particle is actually moving at constant speed, which is typical of circular motion. So the velocity, or the speed, is constant, moving along the outside. And then the acceleration, just take the derivative again, we get minus a omega squared cosine omega t, and then a omega squared sine omega t. And now notice, if I factor out, that's minus as well. Derivative of cosine is negative sine. If I factor out a minus omega squared, then I have a cosine omega t, a sine omega t, but that should look familiar. This is just minus omega squared times r of t. And we've already seen in a previous problem in a previous section that if we're moving along a circle or a sphere, the position and velocity are going to be orthogonal. But this says that the acceleration is in the opposite direction of the position vector, meaning that the acceleration is pointing in towards the middle of the circle. That's what's actually keeping us in circular motion. And so that, we just sketch a picture real quick. So here is R. Here is R prime. So the acceleration is actually pointing in towards the center of the circle in the opposite direction and scaled by the angular velocity squared. So it's also going to be perpendicular to r prime. I mean, alternatively, you can just do the dot product. And show that you actually get 0.